Okay, so we're on the record, so we can go whenever you guys like.
Perfect.
Okay, welcome to the Physics Colloquium. Today the speaker is Professor Andrea Pocar from UMass, and I will really, it's a pleasure to make this short introduction. Andrea is originally from Milan, where he actually got his laurea in Italy. After that, he did a PhD in Princeton, working in Borexino, and spent a lot of time working in Princeton as a student, as a postdoc. After that, he went to SLAC to work in EXO collaboration. That is also an important experiment for neutrino physics. And since 2009, he has been at UMass as a faculty. I have the pleasure to work with Andrea as the both conveners for the SNOMAS process that is now very active here in the US. Then Andrea, please.
Okay, thank you, Pavel. Thank you, everybody, for being here. So this talk is one of those talks that you tend to give when you're aging, I guess. And so this is a talk that will sort of present and summarize the Borexino legacy, both the science it has done. It will give an idea of what it can still do, and it will introduce also some accounts of my personal sort of take on this experience that began for me in 1998, although the experiment started earlier than that. In fact, Borexino started 3 decades ago as a concept to uncover the mysteries of neutrinos and of how the sun shines. It has definitely defined my career so far, sort of at every stage of the way. I'll obviously present the science Borexino has done, some of which will probably stay for a while, I will include, as promised, some personal stories about all this. The synopsis is I'll have to introduce particle physics and neutrinos within particle physics, and a little bit about the sun and what we know about the sun, define what solar neutrinos are in the context of the neutrino oscillation paradigm. Then I'll go and explain the Borexino experiment, the why, the when, the who, the how, the what, the making of the detector, the results, and what else has to be done, with some outlook on this process. This is a story that begins in Italy, under the Gran Sasso range, which is shown in this picture that I took a while back from a plane. And the Gran Sasso lab, where the experiment is housed, is beneath this range. And for reference, the Adriatic Sea is behind you, and Rome is far in the distance to the west. From the air, there's the mountains look like this, and there's a tunnel approximately halfway, of which there's the entrance to the lab. And I also offer a picture that I happened to take from the Rome airport on a particularly clear day one day I was arriving in Rome. So how'd you get into the lab? First, there's a highway and there's a tunnel. This is unlike other experiments. I have to go to uncomfortable places like mines, which are certainly less accessible and harder to work in. Then you go very fast in the tunnel, like shown in this picture. You shouldn't go fast, in fact. There's a limit for the speed, and at some point, there's signs that indicate a turn into the lab. You see some sort of ominous big door that could be out of a spy movie. And once you're in, there's more tunnels. And then there's 3 big caverns, in one of which there's the Borexino detector. The characters are the neutrinos and the sun. Those are the main protagonists that are sort of the things we want to study. The detector has scintillator, has containers made out of thin plastic, Pmts, and fluid purification plants. Important things about the detector are how much light you can get out of the detector and detect. You want to read out signals quickly. You want the detector to be super clean, super radio clean, in fact, and you want it to be leak tight. The villains, our enemies, are radioactive backgrounds, such as uranium and thorium, gamma rays, muons, and radon and its progeny. And of course, the Borexino collaborators, its scientists, technicians, engineers are the success story of this experiment. So why study neutrinos from the sun? Well, this is really one of the big success stories of the 20th century, certainly not the only one, but a very well-defined one. These are the direct messengers of what's going on in the core of the sun, the only thing that really comes out that we can look at directly without delay, without deterioration through many, many interactions like for the photons. And as such, they're probes of the composition of the sun and of its core, essentially. At the same time, solar neutrinos have been part of the discovery of neutrino oscillations by the solar neutrino puzzle, which I'll briefly define soon. And they're fantastic probes of new physics because the sun is actually a very, very intense source of these particles. Looking at the sun, though, the fact that neutrinos are emitted in the sun is a rather recent discovery. And a little more than a century ago, when there was no quantum mechanics yet, the age of the sun was estimated to below 20 millions of years, because it was thought that it would have to burn chemically like fire. Darwin put a little bit of a wrench in this through the evolution of species theory, because he aged the Earth to more than this age, and so the Earth being produced with the sun in the solar system, this was a conundrum or a puzzle. And then the discovery of radioactivity, which was one of the puzzles that made quantum mechanics possible and accepted, identified a possible alternative source of energy, of power for the sun. Chamberlain, at the end of the 19th century, allowed for the possibility of atoms to store enormous amounts of energy, what we now call nuclear energy. And in fact, a native of Amherst, Boltwood, through the lead decay series, dated the Earth in the thousands of mega years for the age of the Earth. So this is billions of years now, which is getting us in the ballpark of what we know today. So this is in a very fast sequence what the sort of initial dating of the sun were. Now we know an enormous amount about the sun. Telescopes have been observing the sun, measuring its energy output in light, in heat, in radiation from the surface, and missions like the Parker probe and the solar orbiter will tell us even more about the sun, say from the outside in. However, the solution of how the sun is burning and why it can be the age that we know of came in the 30s, thanks to Bethe and von Weizsäcker, who developed the theory by which protons in the sun fuse into helium, and through the equation equals mc squared, the difference in mass was available for energy, for the burning, and for these reactions to actually proceed under the appropriate environmental conditions. In fact, two mechanisms of fusion in the sun were identified: the PP chain, which I'll show in a couple of slides, and then in a subdominant fashion, the Cno cycle, which is a catalytic process by which the same fusion process we now know can occur. Particle physics back then was much simpler, was much more rudimentary than what we know today. We know today that neutrinos are part of the leptons. They're partnered with the charged leptons, the muon and the tau. We know that there's 6 quarks. We know about the weak interaction. We know about the forces: gravitational, electromagnetic, weak, and strong. We've discovered the Higgs. So now we have a very clear encyclopedic picture of what is happening. Back then, the picture was not as clear. humanity knew about electrons, photons, neutrinos had just been discovered, postulated, I should say. The neutron had just been discovered, and the positron also had just been seen. So the picture was not as clear as it might appear today. And in fact, the neutrinos were postulated by the need to preserve the conservation of energy in beta decay. And so the neutrino is this third particle that carries away energy and angular momentum, I should say, which would allow these laws to withstand. And so Pauli's idea in 1930 is what we now accept as the start of neutrino physics. Soon after, theoretically, the neutrino was embraced, and Fermi developed the first theory of weak interaction. And we now know that neutrinos of 1 MeV scattering off electrons do so with a cross-section that is indeed very, very small, on the order of 10 to the minus 44 centimeters squared. So while the neutrinos interacting via the weak interaction, as we now know through W and Z exchanges, are an incredibly clean probe of physics, they are experimentally rather hard to detect in large statistics. So the neutrino, or the antineutrino, was discovered at Savannah at a reactor through the inverse beta decay reaction that is well known at Case because of Ryan's stay after his stay at Los Alamos. And this slide illustrates the experimental strategy to be able to extract these rare decays compared to the background singles rate of the experiments by detecting the coincident signal of a positron annihilation and decay into photons and the delayed neutron capture on cadmium that also emitted a copious amount of energy in gamma rays and hence was detectable. And so by carving out from the data set these coincident decays, backgrounds was heavily suppressed and the neutrino signal could be extracted. Neutrino experiments were part of a really interesting sort of set of discoveries and confirmations of the theory of particle interactions. Here is a beautiful picture of a neutrino of muon flavor converting into a muon in a charge exchange and in a bubble chamber and creating hadronic tracks as well that can be photographed and seen. And from these tracks, you can extract properties of the neutrino once you collect enough events to study their statistics. The neutral current exchange were also fundamental in the development of particle physics and in the concept of missing energy in interactions that have a neutrino emerging from the interaction point that doesn't interact with the experiment anymore and leaves an imbalanced, from the energy point of view, event in the detector. And this, collider experiments have used this extensively since. This is a modern day tracker from microboon in liquid argon, and you see a neutrino beam producing again a muon, and the clarity with which now these tracks, instead of being photographed by a camera, can be recorded by electronic data acquisition to give a flavor of sort of how neutrinos at accelerators are now utilized. This is a long set of milestones of where neutrinos played a significant role in the development of particle physics, starting in the 30s till this date. I won't go through all of them. I've illustrated a couple in the previous slides. I'll illustrate a few more relevant to this talk in the next slides. But essentially, the neutrinos have helped progress in fundamental symmetries. They're now in the realm of precision experiments to measure the parameters of the theory precisely and seeing possible deviations from expectations for new physics. And they're now becoming an applied tool in applied science. Curiosity, the neutrino is the Nobel est of particles with 4 prizes, 3 full prize equivalents, and 8 scientists recognized for neutrino-related discoveries. So solar neutrinos are an iterative success story. They helped astrophysics and discovering how the sun works. They made the solar neutrino puzzle emerge that led to the discovery of neutrino flavor oscillations. In turn, neutrino flavor oscillations had to be included in the astrophysical observations. And so these helped then probe the stellar environment better. And so this cycle sort of has continued over decades of experiments. And what is now to be done is that there's a little bit of tension in the definition of heavy elements in the sun, elements it's of weight 3 or more, and also in performing searches of neutrino non-standard interactions, for example, neutrino magnetic moment and other sort of new physics that can be explored once you know the source and the behavior of neutrinos exceedingly well. This is a slide to honor Ray Davis's and John Bacall's experiment in Homestake for the discovery of neutrinos from the sun. These are neutrinos of electronic flavor capturing on chlorine and producing argon that was then the X-rays of which were detected in encounters. And the success is that neutrinos from the sun were clearly identified in roughly the number that had been expected, but not quite. And in fact, only about 1/3 of the expected rate was observed. And this opened up the era of the solar neutrino puzzle that lasted quite a bit. Before going to how this was resolved, let's go into detail about what we know now. So we know that the PP chain in the sun fuses protons, 4 of them into helium-4, and this should be a +2 positrons and neutrinos along the way, plus energy and kinetic energy of the particles. And neutrinos are emitted in all the boxes in color. There's the PP neutrinos, the PEP neutrinos, the beryllium-7 neutrinos, and the boron-8 neutrinos. In addition, there's the HEP ones, which have not yet been observed because they're so few. As promised in the sun, a catalytic cycle involving carbon-nitrogen also can fuse protons in helium, and this accounts for about 1% of the energy generation in the sun. However, in heavier stars, actually starting from about 30% more than the sun and above, the CN cycle becomes a dominant mode of fusing protons. And so studying the CNO cycle and measuring it and possibly studying it precisely in the sun is a way also to measure the parameters of a large population of larger stars around us, and hence an incredible tool for astrophysical studies proper. Now, the neutrinos emitted in the reactions I've shown earlier have an energy spectrum. Some of the emissions are a continuous spectrum because they're essentially beta decays. Well, they're all beta decays. Others are monoenergetic because their decays go through electron capture, like the beryllium-7, and are shown in this chart as thin lines. And you see how their flux is on the log scale, spans a very wide range. The PP are the most abundant, yet the lowest energy and the hardest to detect. The boron-8, on the other hand, are the easier to detect, but they're much, much fewer. And so experiments have mapped this and measured chunks of this spectrum, as shown in this chart. And you see the chlorine experiment had a threshold at just below 1 MeV. Other radiochemical experiments on gallium had a much lower energy threshold, so included a large fraction of the PP neutrinos. The Cherenkov experiment, like Kamiokande and Super K, only measured the tail end of boron-8, but that was actually enough to discover neutrino oscillations, among other things. And so the solar neutrino puzzle, that is the fact that every experiment up to the end of the 90s had seen missing neutrinos from the sun in different energies and at different stages of that PP chain, was a big puzzle, because the fact that boron-8 neutrinos had been detected meant that beryllium-7 neutrinos had to be there. Otherwise, the other ones would not be produced either. The final solution of the problem came with the Cno experiment on deuterium, where they could measure both the pure electron flavor spectrum from the sun and the total spectrum from the sun, that is any flavor that's active, E, mu, and tau. And they actually saw a difference in flux between the two. And this is illustrated by their famous plot, where they plot the flux of electron flavor and the flux of combined other active flavors, the mu and the tau. Their sum is constrained. That's why there's a diagonal band. The red is the purely electronic flavor. And so the solution is that as they emerge from the sun, only a third of the neutrinos remain of electronic flavor, while the others have transmuted to the mu and tau flavors as they travel to Earth. And that's how they're detected on Earth. And then some detectors will miss them if they're only sensitive to the electron flavor, like the chlorine experiment and the gallium experiment. Super K 2 years earlier had discovered neutrino oscillation in the atmospheric sector from neutrinos emerging from pi and decay, and they saw a deviation from the expected factor of 2 between muon flavor and electron flavor in the showers of cosmic rays. Borexino. Borexino, by the early 90s, had actually been proposed as one of the possible solutions to the solar neutrino problem. It was targeting the detection of beryllium-7 neutrinos. I just said that neutrinos from that reaction had to be present, although there was no room for them in the overall rates measured by the various experiments. And so a clear detection of those very neutrinos was a detection, would have greatly improved the understanding of this issue. Borexino, though, took a while from design to concept to prototyping to actually run. And by the time it ran in 2007, neutrino oscillations by Cno had been established. Nonetheless, the experiment was extremely precious, both for neutrino physics and for solar physics. This is a picture from the early days, just to give an idea of how the collaboration started in '93 at Princeton with a prototype of the nylon balloon that then became sort of one of the great new ideas in how to design these detectors. Schematically, Borexino is a large sphere of liquid scintillator at the center and contained in this thin nylon balloon and kept sort of pressurized into a spherical shape. However, because of backgrounds, this core of 300 tons of liquid scintillator that allows you to measure the low energy neutrinos, contrarily to the Cherenkov technique that has a high energy threshold, has to be shielded by layers of cleaner and cleaner fluid as you go from the center outwards. And so there's about 700 tons of organic buffer fluid, then a sphere on which the Pmts are mounted properly further out from the core so that their radioactivity is separated from the core of the detector. And then this big kiloton sphere is immersed in a water tank that provides further shield from the rocks of the cavern, and it acts as a muon detector to tag possible sources of background. The main technique is neutrinos come in, scatter off electrons, the electrons recoil in the scintillator and produce a flash of light. That flash of light can be measured in intensity, and the triangulation of the time of arrival of the photons allow us to reconstruct the position to within about 10 centimeters at 1 MeV at the center of the detector. The detector is installed in Hall C under the Gran Sasso mountain. I've shown the lab earlier, and here's a picture of the actual Hall C from the Borexino tank, from atop the tank. Prototyping took place in the 90s. The CTF, the counting test facility, proved on the ton scale facility that the purities of radioactivity intrinsic to the scintillator in uranium, thorium, and the isotopic abundance of the carbon-14 beta emitter, these are all providing backgrounds to the rather free of topology electron scattering event in our detector where possible. So uranium and thorium were measured at less to 1 part in 10 to the 16 by weight, and the isotopic abundance of carbon-14 for the scintillator sourced from petroleum that had resided deep underground for very, very long times was proven to be adequate to set an energy threshold and to prevent pileup of events in our experiments that would allow the detection of the beryllium-7 flux. This is a picture of our sort of the key parts of our experiment. On the left, the Pmts with their concentrators. These were all screened for low radioactivity. And Borexino, I would claim, is probably the first experiment that did very, very systematically the radio assay of materials that now is commonplace for all detectors searching for rare events underground in this kind of large detectors. On the right, you see the nested set of balloons that we built at Princeton after they were installed and inflated and before we closed the stainless steel sphere. Then we filled the detector with, we did a water fill first. We took beautiful pictures of these processes. Then we started inserting liquid scintillator from above. It floats on water, and we displaced the fluids from top to bottom. And you get some great pictures and some great optics that you can try to understand. The scintillator came by truck from it came on tanker. The tanks came by ship too close to Rome and then trucked up to the labs quickly to avoid activation of isotopes inside it. They were unloaded, distilled, purified, gas stripped, and put in the detector already very clean, as illustrated in this cartoon. This is a kind of tank the scintillator came in from. This is the so-called unloading station of it's a set of pipes that were all meticulously leak checked and cleaned to avoid picking up radioactivity in the fluid. And this is a picture of the detector filled in May of 2007. And here is where the science of the experiment starts. Now, let me say a few things. I joined the experiment in '98. I worked mostly on radon issues and the fabrication of the nylon balloons. I lived in L'Aquila for a while, but there was an accident. Some scintillator actually spilled in the local creek, and the experiment was halted for a few years. So I had to change the topic of my PhD dissertation. But that all worked out, and then I moved to Stanford in 2004, but was still able to remain connected to the experiment, awaiting its science output. I will say that these were dark days, and in fact, very prominent scientists didn't necessarily have good things to say about the experiment. Borexino will never reach the purity that it wants. Hall C is not as clean as Snow Lab, and a young scientist saying, I don't say that I worked on this experiment much in job interviews because it's not a good thing to say. So these were hard times for an experiment that fortunately turned out to be extremely successful. These are images of the fabrication of the balloons at Princeton, a large clean room. This is Pocar. I'm taking him around for a tour. And on the bottom right is the set of 2 vessels properly bagged multiple times and packed and ready to go on a truck, then on an airplane, and then to Italy. We celebrated when we were done with the fabrication of the vessels. I worked on radon suppression. This is the filter I built as a student at the early part of my PhD. This was the first demonstration, prototyping, and use of a radon scrubber for clean room of this type. Now this is rather commonplace. Every experiment kind of has its own. So this is interesting to document. And for the sake of this talk, I dug out some old talks. These are the first talks I gave as a grad student on these concepts, talks I gave at the APS and other conferences, still on plastic slides. And to just say how radon never goes away if you're an expert in it, this is the same type of filter I built for EXO 200 in 2013 in the WIP salt mine. And so again, I was hoping never to do this again, but I guess it's still an issue for these experiments. These are curiosities. In order for the vessel production, we established procedures for surface cleanliness that were very new to our field. And so I spent many hours on end doing particle counting of cleaning procedures by putting filters under a microscope and counting the number of particles of a given size, and then using military standards to classify the cleanliness of the surface, et cetera, just to give an idea of the kind of things the success of the experiment had to go through in order to be achieved. The vessels were prototyped, and here again, I dug up pictures from the old days of the kind of things we did, and then eventually we inflated prototypes in the Princeton gym, the only space that was big enough and from which you can actually hang things. These are pictures of the installation in Gran Sasso. The roll is unrolled, uncovered, unbagged, lots of precautions. And this is the vessel being installed inside the stainless steel sphere. And you'll see how this has been done with the PMTs mostly in place already. And so the kind of care that had to be put was extreme. Well, this had a good ending. I graduated, and this is me at the end of the installation in the sphere, happy to have the balloons installed. The thing that is not apparent from these pictures is that we're still in a lockdown, so we couldn't operate the experiment, and we didn't know if the experiment would ever have run at that point. Little trivia pieces. I actually had the displeasure of having to cut open the external balloon after having built it and leak checked it meticulously, because we had to fix some ropes inside. And so I was tasked with actually cutting it open, which was very painful to do. There's other things that happened. If you work in a tunnel, accidents do occur, and trucks do catch fire relatively regularly. And this is well known, and it's established also in other tunnels in the Alps and elsewhere. And there were some close calls. And so safety on the ground is something really not to forget. Not just the safety of the experiment, but the safety of people. And then mountains are typically in earthquake-prone areas, and L'Aquila was hit hard in 2009. So I can't say our experiment has had an easy start. Nonetheless, we were able to survive all this. And so let me come to the science that we were able to do. On the left is the plot of the solar neutrinos emitted by the sun. On the right is the spectrum of the main components of the electron scattered energy that we actually see. So a monoenergetic line appears in our detector as a Compton edge of scattered electrons, like the beryllium-7 in red or the PP in purple. The PP and the Cno are continuum, and so of course they stay such. It needs to be underlined that we lose most of the directional information in the scintillation process. The scintillation is isotropic, and I'll say more at the end of this talk. This is a timeline of what we did. We filled the detector in 2007. We ran a phase 1 for a few years. We did the first observation of beryllium-7 neutrinos. We measured the absence of day-night effect for these neutrinos. We did the first observations of PEP neutrinos. We measured the boronate neutrinos with the lowest energy threshold. We set a limit on Cno. We measured antineutrinos from the Earth. We did some exotic physics. Then we decided to purify our scintillator and reduced krypton-85, bismuth-210, polonium-210, thorium, and uranium. And now uranium and thorium were at the level of 1 part in 10 to the 20. Hard to believe when we started or when we proposed the detector. We ran phase 2 for the next 4 years. We measured the PP neutrinos in real time, event by event, for the first time. We did seasonal modulation verifications. We improved all the measurements of the PP chain, and we improved the neutrinos observations, and we did set a limit on the magnetic moment of neutrinos. And then we set off for the Cno campaign, which is our last sort of success. This is kind of an idea of the kind of purification the scintillator has gone through. I won't go into details, just to say that suppression factors were visible and significant. We had, of course, to calibrate the detector, and this was done with very, very clean sources inserted in the detector with a mechanical arm at various gamma energies. We had a radon source in a vial. We did all sorts of things in many, 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 many positions in the detector that allowed us to really define the fiducial mass of the detector, the response function of the detector in terms of energy as a function of position, and so on and so forth. And these are the things you typically spend the most time on. This is the data as it, as it appeared at a first look. And this illustrates how we look at data. The black spectrum is what you see if you just plot all reconstructed events. Then you apply muon cuts with the veto, and this cuts a lot of the high energy part of the spectrum. But the big improvement happens when you go from 300 tons to 100 tons, making a fiducial position cut on your data, and then rescaling it, of course, to this plot. And now suddenly you see features. You see the carbon-14 beta spectrum falling off on the left. You see the beryllium-7 Compton edge starting to appear. You see a prominent alpha peak. It turns out to be polonium-210. And then there's this carbon-11 bump. Carbon-11 is a cosmically activated isotope of carbon, lives half an hour. You can't veto it with a muon trivially. You have to do a more complicated procedure to do that. And it's a beta plus emitter, which is why the spectrum is offset from the origin. So this is what we do. And then if you apply a cut for the carbon-11, you get the green spectrum, which allows us to do more physics, as I'll try to illustrate. This is, again, the real spectrum with all the components sort of identified. You see the beryllium-7, the PP, the CNO, the PEP, and the boronate. And then in blue are gamma rays from the outside leaking into the fiducial of the detector, and then the purple is actually pileup of carbon, of mostly carbon-14 and polonium-210 events. And in a snapshot, these are the measurements that we were able to do in phases 1 and 2. And so we measured the beryllium-7 neutrinos to better than 3%. The goal was to do better than 5 or 6. We measured PP at 5 sigma. We measured the PP neutrinos at to 10%, and B8 confirmed the measurements of Cno and super K especially. And then we set a limit for the HEP and the CNO components. And of course, these numbers in green are the rate that we see for each component. Then we fold in the large mixing angle neutrino oscillation parameters and reconstruct what the flux that we infer from it is, and compare it then with the theoretical flux for each piece. And you'll see how the theory has two values which depend on the abundance of heavy elements in the sun, which greatly affect mostly the CNO component, but not only. More about me. As a postdoc, I stay connected to this science. Of course, I wasn't paid to stay on the experiment, and so I took shifts on my time off. And of course, that paid off because I had a running experiment when I was searching for jobs. And I think that sort of was a good thing. But more so, I participated in the science output of a beautiful experiment. These are snapshots of the other things we did. You see the modulated signal due to the eccentricity of the Earth's orbit and the varying solid angle of the sun from the Earth. Below is how a magnetic moment at 510 to the -11 magnetons would look like, distorting the beryllium-7 electron scattering spectrum, just to give an idea of how we search for these effects. There's papers, of course, on this. Other details is when we did the measurement of the PP neutrinos, you see how this is mostly buried under the carbon-14 beta spectrum, which is even at 1 part in 10 to the 18 isotopically dominates the trigger rate of the experiment. And in order to do that, we had to really study the pileup of the experiments that we hadn't had to do until then, because in order to have the red line emerge in this spectral fit in the valley between the alpha peak and the carbon-14 peak, we really need to account for all possible components. And this was a data-driven technique that my student here at UMass figured out and implemented. At the same time, we did the second or first, depending on the significance you want to take as threshold, observations of neutrinos from the Earth's radioactivity, uranium and thorium. And you see here the excessive events. And we also, at the same time, did the observations of reactant neutrinos from about 1,000 kilometers away from reactors in France and Switzerland, which was an interesting sort of technical feat that we were able to accomplish. But looking back at solar neutrinos, we then focused on the missing piece, the Cno, which was the important piece at that point. And in order to do that, you see how the sensitivity to Cno, given the fact that we have the beryllium-7 neutrinos, which dominate here on the left, and then we have the nasty carbon-11 background, which even after subtraction is still present, leaves a little bit of a window around this sort of MEV or just below energy for the emergence of the Cno spectrum. However, the green line shows that one of the backgrounds that we know we have in the detector is bismuth-212, a child of lead-210 and producing polonium-210 is also in there, and it's a beta spectrum that we need to resolve. Now, it's almost impossible to resolve it just by the spectral fit, and so we need another way to try and do it. But now, let me just focus on why Cno is important. As I said, this is a catalytic cycle for fusion. It affects a plasma opacity, indirectly affecting the core temperature. So it's an interesting solar coupled problem, and it's one of the parameters that is needed. And different measurements from spectroscopy and helioseismology tends to prefer different values of the abundance for these elements with a gap. And so the measurements of neutrinos is a direct way to possibly address this issue. However, the expected rate is in the few counts per day per the nominal fiducial 100 tons of scintillator. And so the idea here is to find a constraint for bismuth-210. Now, we have a constraint for the PEP component, which is also there, because we know what PP is, and we know that the ratio of cross sections of PP and PEP we can take from known nuclear physics and apply a constraint in our spectral fit. But what did we do for bismuth-210? Well, the idea here is bismuth-210 might at some point reach an equilibrium with polonium-210, which would indicate that it has reached a secular equilibrium from lead-210, bismuth-210, and polonium-210 in the detector. However, as you remember from the spectrum I've shown, the alpha P from polonium-210 changes drastically in time, but it turned out that it didn't change with the intrinsic half-life of polonium-210 to an asymptote, which is what we were trying to aim for. Had it reached an asymptotic value that was stable, that value would have been the secular equilibrium activity of anything above it up to lead-210. But what we observed is that polonium varied in time up and down in the fiducial scintillator. And we realized that this was because of convective motions in the detector. And so we set off to thermally insulate the detector. And we did so with home insulation of the type you might choose for your home. We also added a heater at the top of the detector to force a gradient of temperature that would be as stable as possible and would prevent mixing of the fluid in the detector. And the mixing would pick up background on the outer edges of the scintillator on the vessel and then redistribute it in some hard to model way inside the detector. The installation took some time, and the timeline is shown here. And then the last step of the thermal stabilization of the detector was to control the air temperature around the detector in Hall C via a set of heaters of the input air. Borexino turns out to be a thermometer of incredible accuracy and precision. And you see here how on the bottom plot, we had to top off the detector as it cooled down and the density grew, and hence the head surface would slowly shrink, and we would have to add fluid from the top. But you also see here that 1/100th of a degree is sort of the range that we reached after we stabilized the detector. And this is incredible over this amount of mass. Of course, the mass, once you stabilize it and it doesn't move, then has a lot of, it stays stable for a while because, of course, it stores a lot of energy in it. These are thermal probes across the detector that show the stabilization of the detector that we reached in the various phases of the stabilization. And this is an analysis that shows, as a function of time, and the y-axis is basically little volumes of voxels of detector in which we measure the polonium-210 alpha activity. The alphas we can distinguish event by event by their pulse shape discrimination. Alphas have a very long scintillation decay time compared to beta-like events. And you can see here how a clean volume of scintillator would be at the bottom, then rise and go back down and rise again until we started to insulate the detector. And once we did so efficiently, we layered the fluid, and the central parts of it were extremely low in polonium-210. And in those regions, we could do a polonium analysis to extract the asymptotic behavior of its decay, from which to infer the bismuth-210 activity. Of course, once we did this in a little 20 tons of the detector, we had to then check that we could extend this to a volume which was much bigger than that. And so we did uniformity tests of the beta activity in the region of interest of the spectrum as a function of angle, so essentially a sky map of it, and as a function of radius as we increased the volume of the detector. And we did spectral fits in all these slices and made sure that we had our systematics understood. And we were able to set a limit on the bismuth-210 activity of 11.5 counts per day with a 10% error. With that, we could go back to the spectral fit, use this as a constraint on the component of bismuth-210, and then any excess to that would be Cno. So this is exactly what we did. And of course, the analysis is more complicated than I tried to make it. We did it on the carbon-11 subtracted spectrum. We did it purposely on the carbon-11 enriched spectrum of times of the detector tagged after muons. We made sure that the radial distribution of events was consistent. We had to correct for a vessel that was not exactly a sphere. Remember, it's a balloon, and so it picks up spherical imperfections. But after we did this, we extracted from our master spectral fit with all the constraints as illustrated the Cno rate of 7.2 counts per day with an error in 100 tons. We did, of course, likelihood analysis from which we extracted not just the statistical error, but the systematic errors. We profiled it, and we declared an observation at better than 5 sigma and 90% confidence. Simple counting analysis in that bin gave us confidence that this made sense because it gave us also a good significance, although not the full 5 sigma that this more detailed technique would allow us to do. And so updating the table that I've shown earlier, we can now claim an observation of Cno. However, our observation is doesn't allow us to distinguish the metal content in the sun yet. Its uncertainty is too large. Its central number is too high. So more is needed. However, Borexino was asked to terminate its life in October 2021. This is a leftover of our spill back in 2002, by which the lab agreed to eliminate all scintillator from the underground. This includes the LVD experiment as well. And so on October 4th, we turned off the voltage and the DAQ for the last time in the detector. This was a bittersweet day. However, this comes more than a year after this data is taken. So the CNO published number uses data that ended in February of 2020. After this, we actually did something more with the original phase 1 set of data, and this is the last piece of science I want to inject. We looked back at the beryllium-7 events, and we did a detailed time of arrival of the first photon hit, the second photon hit on the PMTs, and knowing at each time where the position of the sun is with respect to these first hits of light detected in the detector, we correlated whether there was a correlation between the first hit PMTs and the pointing back to the sun. If so, this would be attributable to the tiny amount of Cherenkov light that is also present in these interactions. There's not just scintillation. And the two plots show the sort of arrival time. The Cherenkov are prompt. The scintillation takes more time. The process itself takes time after you correct it for time of flight for position, obviously. And also the spectrum is not the same. Now, of course, the process is complicated because the Cherenkov fraction is actually much smaller than shown here on the plot by a factor of 1,000 about. And the Cherenkov photons themselves could be absorbed and be emitted as scintillation photons isotropically. And so we had to take all that into account in our simulations and in our understanding of this process. But indeed, we were able to squeeze out a directional sensitivity. In the bottom center, it's Borexino data in black, compared with a model of background that essentially is flat compared to the direction of the sun, against a purely solar neutrino simulated signal in red, and then you see in pink the best fit, which has a little bit of a mixture of both. And so statistically speaking, for the statistical sample, we actually were able for the first time to see directional information in scintillators below, for neutrino interaction below 1 MeV. And this was vetted by source runs as well, with which we could do the pointing back to the source exercise. And this is really interesting because while we couldn't really use this in much of the analysis quite yet, is a very good indication for future experiments that might tailor the amount of scintillation and Cherenkov, think of the Theia proposal for the future, by which you could actually enhance the Cherenkov and fast component and hence retain the directional information while still having enough scintillation to keep your energy threshold low. So what's the final thing? The final thing we're trying to do is to improve the measurement of CNO, maybe putting in some directional information as well. We're working on it. As I said, we have more than a year of extra data from what we published. And in fact, that data is the thermally stablest data we've ever had. And so qualitatively, it's not just an addition of exposure, but it's an addition of exposure of data which is qualitatively much better than what we have used so far. I can't say anything at this stage other than my hope is that we will be able to publish a final paper with a better result on this, and maybe hopefully start saying something about the metallicity of the sun. Let me thank my collaborators and spend a memory for those who passed away over the long time the experiment has been active. So concluding, solar neutrinos are have been essential to prove solar fusion and discover neutrino oscillations. Borexino has precisely mapped the PP solar neutrino chain, measured the CNO neutrinos unraveling all the energy producing mechanisms in the sun, confirming the stunningly precise prediction that dated back to the 30s. So theorists did a really good job, as often happens. Not always, but often. Borexino has demonstrated directional capability, paving the way for future experiments. And certainly Borexino, is safe to say, has pioneered low radioactivity techniques, which have now really become commonplace in modern experiments in neutrino and related fields. And this has shaped the career of many back then young scientists that are now active. Thank you so much for your attention.
Thank you very much, Andrea, for this beautiful colloquium. Fascinating. I would like to ask if anybody has a question. Particular the students. I see Ben.
Hi, thank you for the talk, and thanks for coming. Just quick, during the period when you were volunteering on Borexino, did it have US funding at all, or had it been cut off?
No, it did. And in fact, NSF was one of the biggest supporters of keeping the experiment alive. And it had, I must say, a pivotal role with INFN in keeping the experiment alive, I think. Yeah, so NSF really believed in the experiment. They wanted to really do all they could do to try and make it work after the substantial investment that they have made. No, NSF really funded the vessels, funded the purification system. So a lot of the sort of new techniques were very NSF flavored. And so I think NSF can safely bank on this now and say that they really enabled the development of many of these techniques.
My other question, maybe this is me being a vampire. Now that it's decommissioned, where are the PMTs going?
That's a good question. So first of all, I should say that only about half are still alive. And this is not too surprising. I mean, if you read the specs that they had, it's pretty much in line. These were very specially made PMTs with low radioactivity glass made in England by back then EMI, or ETL, I think it's called now. But anyway, it was a very special process made for us. And so they were delicate. They weren't like your standard PMT that you can just throw in. But that said, means that about 1,000 are still alive. I think many collaborators will try to claim one as a memento.
As a souvenir. Excellent.
But if there's any interest at all, you should speak up with Ezio. And at this point, all the infrastructure has been handed to the labs. The groups, gave up the ownership of the plants so that they didn't have to pay the decommissioning, so that it got out of the hands of NSF and other funding agencies. And now the labs can do what they want, basically, with it. They're emptying the detector and they can reallocate it to whatever experiment is interested in having. I doubt a new experiment is going to be interested in any of the PMTs, given that they're old and they have shown to have a half-life that is measured at this point. But so if you have a use for them, you might want to put in an expression of interest.
How?
You write to the director of the lab and you express it, and then he'll tell you if there's a more formal process. Or maybe he'll tell you they're already allocated, in which case.
You have a question,
Yeah, my question is very related. I was trying to ask why the experiment was decommissioned. Is it because all the science goals are unrealized, or just because the equipment are, coming to their lives?
Really not. I mean, a little bit of the former. So Borexino could not have really continued for much longer because the PMTs were dying. And so at some point you lose sensitivity to the processes you want. It would have, our terror was, a star blows up next to us and we're turned off. That is still something that would be a great pity. But as months go by, and, at some point it's going to occur. But it was important to me that it didn't in the next month or two. The decommissioning is really because the lab has committed to eliminate organic scintillator from the underground altogether. It's a negotiation with the local authorities and the environmental groups that this would happen, and we couldn't push it any longer.
Stacy, please.
Yeah, thank you. I'm curious about the distinction between high and low solar metallicity. And so, being an astronomer, I think of this in terms of the oxygen abundance, 12 plus log of H is 8.7 or 8.9. But what really makes the difference here? Is it the higher Z metals, or what are we looking at here?
So let me see. So if I go back to the sun, what we're looking at is mostly this branch of the cycle.
Okay.
And then we would measure the oxygen 15 and the nitrogen 13 neutrinos emitted in these two steps of it.
Okay, so it's really the Cno cycle that's dominating the signal. Okay, thank you.
Sure.
Annette, please.
Hi, yes. I was just curious about the curve fitting for the CNO. That looked like a tough fit. Could you speak to the shape of the curve and
From here, you mean?
Yes. Could you speak to this shape of the curve? What may be going on to make it so that shape? It just seems.
You mean this red shape here?
Yes, that long.
Well, this
yes.
is a combination of continuous spectra. So if I go back to the solar neutrino spectrum, you see how the N13 and the oxygen 15 are these sort of continuous spectra. And then when you scatter these off electrons, the spectrum of scattered electron is a continuum with a known but not particularly interesting type of shape, especially if combined with all the others. And so the distinction of this red line and the green line from the background of bismuth 210, while if you had an access to the endpoint, you might be able to say something if you had enough events. Because the endpoint is buried under other things, and you rely on just the height, the number of events in this bin effectively, then you really have to apply a constraint if you know you have this kind of background.
Okay, yes, because I was a little confused by that, but that makes more sense.
Yeah, it's a really hard component to weave out. I mean, it took a lot of work.
More questions? I have many, but better. Can you say a little bit about the neutrino magnetic moment? Because I remember you guys did a lot. I don't know if you have.
We did a lot, but I think we said what we could. The fact that the PMTs have been dying with time means that we're losing sensitivity in the low energy part. And so even if we have more data, that data is not really adding much to it. And so I think what we said is said, unfortunately.
Too sad. Any other question? Okay, we can keep talking, but let's finish the colloquium. Thank you again for the nice colloquium. Thank you.
Thank you all for